All right, here we go. We're going to throw some more rules at you. So if you don't know all your rules so far with your translations and your reflections, man, I would stop this video. I'd go back and rewatch those or do some more practice because you need to have those down before you get to these stretches and shrinks. Otherwise, we're just going to make things way more complicated. And we're going to introduce a new family here, which we'll start with right away, our absolute value family. So remember, absolute value is the distance a number is from 0. So for example, if I took the absolute value of 4, it's 4 units from 0. If I took the absolute value of -4, it's also 4 units from 0. So we can't have a negative distance. So anytime we take an absolute value, we always get a positive. So before we answer these function, domain, range, let's take a look at it on a graph. So I'm going to go to my calculator here, and let's go ahead and graph this guy. Well, I need those bars. And if you take a look, there's nothing I can just type in for a button. So what I need to do is, I'm going to go and do my math, right, because I got a lot of cool things in my little math stuff here. And we got this thing called num for numbers. So this deals with different types of math numbers. And if you notice, we got ABS for absolute value. So I'm going to select that ABS. And if you notice, it just puts those bars just like that. Perfect. So I can just hit my X. So that'll take the absolute value of X. Let's go ahead and graph this bad boy. Oh, gross. Don't do that. Get some negatives in there as well. So make sure zoom standard, right? Get it back to your -10, 10, -10, 10. There we go. That makes more sense. So if you notice here, my parent graph does not go in to any negative y's, right? And that should make sense because, if I plug anything in for x here, it's always going to come out with a positive. So if we take a look, is that a function? Well, yeah. If I do the vertical line test, boom, 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 it crosses at 1. So each input has one output. So is it a function? You bet it is. What's its domain? Well, is there any x value that I can't plug in there and get an output? No. And if I look at my graph, it seems like it goes on forever in the left and right direction. So the domain, the x values, are basically all real numbers. Everything works. There we go. And we have a little symbol for that. We could put a capital R with a little line. That represents all real numbers. I'm okay with that as well. And what is its range? Well, for the y values, we just said, it can't be any negatives. It goes on forever in the positive direction, right? Both this way and that way. And does 0 work? Yes, right? 0, 0, if I plug in absolute value of 0, that's 0. So that does work. So its range starts at 0 and it goes on forever. So we would say our y's are greater than or equal to 0. And if we take a look, I got a graph right here. So the biggest thing, same thing with like parabolas and things like that, is that our square root family, it's good to know at least 1 or 2 points on each side. So for example, 0, 0 is kind of the vertice here as it goes. And if I notice, if I plug in a 1 or a -1, I get 1. So I got that graphed. So these are some key points to know. That's going to help you adjust your absolute value graphs when you shrink or stretch them. Okay, so that's important. Plus, if we translate them as well, we need to know that, right? If I plugged in 2, I'd get 2 as well, or -2, I'd get 2, so on and so forth. But we need to know that 1, 1 and -1, 1 for that parent graph. That's very important. That's going to help us. So far, everything we've done has been rigid transformations because they produce an image that's congruent to the pre-image. So translations and reflections give you congruent images. They're just shifted or flipped, right? But they're congruent. They're the exact same size. A non-rigid transformation is when they're not congruent. So that's what we're going to do today. We're going to stretch or shrink our parent function, which is going to make it not congruent to the parent function. And we'll take a look at that here with our absolute values. But it can be done to all our other ones. It can be done to parabolas. Our quadratic family could be done to square roots, our radicals. Okay, but we're just going to introduce it here with the absolute values. So right here, let's graph these two guys. And then let's take a look, how has the graph changed from the first? So let's grab my calculator. So I already got the square root, or the absolute value of x. That's good. So let's go back in, down here, and I'm going to go 2 times the absolute value of x. So I could take it times y1, right? I could go into my variables and grab y1. I'm going to do my absolute value again so we get used to it. So math, over to numbers, grab my absolute value, and we got x. All right, so let's go ahead and graph that guy. So it looks like it stretched it vertically. everybody see that? Stretched it vertically. And that should make sense, right? If I made a table of values here for my x, y, it starts off with 0, 0, and then if I plug in 1, the absolute value of 1 is 1, and 1 times 2 is 2. Right? If I plugged in 2, I'd get absolute value is 2 is 2, and 2 times 2 is 4. Same thing if I did negative 1, I get the exact same answers as its opposite there. So negative 2 would also be 4. So let's think about how that got adjusted from our parent graph. So our parent graph started with 0, 0, and then what happened to when we multiplied by 2? Same thing, still right at 0, 0. But then our points 1, 1, and negative 1, 1 got adjusted to what? Well, it went to 1, 2, and negative 1, 2. So if we notice, our y's basically got multiplied by 2. And if we take a look here, where does that come from? Right there. Or we could really say they stretched. Another way we could word this is they stretched by a scale of 2. By a scale of 2. So my equation, I'm going to write this up here. Y equals 2 times the absolute value of x. Could I rewrite that a different way? Could I have that 2 on the other side? Sure, I could divide by 2 and put it on the other side and say y over 2 equals the absolute value of x. So in either case, if I have the 2 being multiplied in front of the absolute value of whatever's inside there for the x, that means it's going to stretch it vertically by 2. Same thing if it's over by the y, if it's being divided by 2, it's going to stretch it vertically by a scale of 2. So the y's get multiplied by 2 basically. And we'll look at that more in depth here in just a second. But what if I did it to my x's? What if there's something done to my x's? Let's go ahead and graph these guys. So we'll get rid of that. So let's grab math, absolute value, x divided by 3. Enter. Okay, let's go graph that guy. So there's our parent function. There's our new one. So now it's stretched it horizontally. Stretched it horizontally. So let's think about our points here. So I'm going to grab our key points, right? Or our key points are the vertices, so 0, 0, and then 1, 1, and negative 1, 1. What about with this new guy here now? Let's look at our table. We got 0, 0. What happens if I plug in 1? I get 1/3. What happens if I plug in negative 1? I also get 1/3. Well, let's get an integer for y. What would be my first integer if I plugged in what? 3 for x and negative 3? That would give me 1 and 1. Okay, so let's think about what occurred here. So we went from 0, 0 and 1, 1 and 1, or negative 1, 1, to what? To now this guy, we have 0, 0 still, but then how did that first point get shifted? It went to 3, 1, and then negative 3, 1, right? It's good to look at the ones with the integers. That's helpful. So what happened in this case? It looks like our x values got multiplied by 3. And that's in this case right here. So it's stretched horizontally now. So I'm going to state that up here. Stretched horizontally rather than vertically by a scale of 3. We see that? Okay, so that's where this comes into play. So if we replace y with y divided by a, or basically we just divide the y by a, it stretches our graph vertically by a factor of a, or a scale of a, we could say. So we looked at that first one, right? We had y equals absolute value of x, and if I divided the y by 2, it stretched it by a scale of 2. Which means all that happened is we take a point from our parent function, like 1, 1, and what do we do to the y? We multiply it by 2. So that would become 1, 2 on our new graph right there. And remember, it could be on the other side. Remember that 2 could be multiplied over to the other side? So you could have y equals 2 times the absolute value of x, right? More than likely, you're going to see it this way the majority of the time. Just know that that's where our vertical stretch of 2. So you're multiplying all the y's by 2. And the opposite true is when we divide the x by something. Now that's going to stretch it horizontally by a factor of b. So we're multiplying all the x's by whatever that is. And we just took a look at that. We just had, here was our parent function. And what did we do? We divided the x by 3. So it multiplied all of our, so our 0.11 here, it multiplied the x by 3. So that became 3, 1. It moved it horizontally. Okay, so we got to get used to that. So let's take a look. Here's my parent function, and now let's write equations. So if this is my parent function, it's important to know your points, 0, 0, 1, 1, and negative 1, 1. You got to get those down. Okay, so since this guy is still at 0, 0, it did not shift left or right or up or down. Okay, I got that. I could move these left or right or up and down, and the same rules follow. For example, if I move this guy right, you'd have something like x minus, whatever you move it the h direction. Okay, so all those rules work. But let's take a look. So from 1, 1, we move to 2, 1. So is that a horizontal stretch or a vertical stretch? That's a horizontal stretch by a factor or a scale of 2. So how does that work for horizontal stretches? We take our parent function and we just divide the x by 2. So that would be for this equation right there. I could graph it on my calculator to check, but I don't think I need to in this case. Well, now let's look here. It looks like it's got stretched vertically, but remember, just deal with those same points. So 0, 0 did not shift right or left or up or down. And then my 1, 1 jumped up to 1, 2. So what happened to the y? It went from 1, 1 to 1, 2. So what did we do to the y? We multiplied it by 2. So this one has a vertical stretch by a scale of 2 or factor. Either one's fine. So what happens there? That's our y divided by 2 equals the absolute value of x. And remember, the other way I could write that is put the 2 on the other side. I could say y equals 2 absolute value of x. Either of these are just fine. Okay, either one's just fine. Separate those right there. Okay, they mean the exact same thing. All right, let's do it with something that's not an absolute value now. Let's try it with a parabola. Okay, this is where it gets tough, when it gives you a shifted graph. Okay, so in this first one, this guy is shifted right 1. Because with our stretches, whether it's a vertical or horizontal stretch, we want to consider that before the shift. So do stretches before shift. That's important. Write that down. Put it in your notes. Do the stretch before the shift. So what I want to do is I'm going to draw my parent graph back in here because that's going to help me out. So 0, 0. I might even make my table for my parent graph over here. So y equals x squared. So remember, we got 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. So I'm going to go ahead and graph those. So 1, 1, 2, 4, negative 1, 1, negative 2, 4. So there's my parent function. So that's important. Okay, so when I look at C down here, this is where it gets tough because I want to consider the stretch before the shift. So I might even draw my parent function in just so we can see this a little bit better. So how did it get stretched? Well, just consider that first point away from the vertex. So here, I went from 0, 0 to 1, 1. So this got stretched horizontally, correct? So this had a horizontal stretch. So what I want to look at my x or my y? Yeah, we're just really considering our x right here, right, for the horizontal stretch. All right, so let's see. How did this thing get stretched? Well, if I look at the new graph, here's my vertex. The parent graph would be right here, 1, 1. It looks like it got shifted over one spot. So really, this guy was stretched just like this and just like this. So what did it do to the x? It multiplied it by, well, this point right here is 1, 1. So to get the new x, this guy's at 2, 1. So it multiplied by 2 times 2 to the x. So it has a horizontal stretch by a factor of 2. And then it gets shifted. That's where the tough part comes into place. Because if I even look at this point is at 2, 4. Well, if I multiply the x by 2, I'm at 4, 4, 4, which is right here. And then it gets shifted 1 to the right by that minus 1. So that's really hard to comprehend. I get that. So if we think about this, it was y equals, well, we had a shift of 2. We had a stretch of 2, right, squared for our parabola. And it shifted 1 to the right. So I have to have that minus 1 in there. So that was pretty tough. Okay, that's probably that's one of the best ways I think I can describe it. So just try to think about the stretch before the shift. All right, so let's go to this next one. Maybe we can see it a little bit better here over here. So this looks like a vertical shift. So I'm just going to write that. Our vertical stretch, my fault, sorry. Vertical stretch. Let's figure out the scale. Well, I'm going to consider my parent function again. So my parent function was 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. There we go, just like that. So I'm just going to look at how this got adjusted for this first point. So this was 1, 1. So what happened to my y with this other graph? Well, before the shift, it looks like from the vertex, when it goes over 1, it goes up 1, 2, 3. So before the shift, this guy was over here, and it went up 3 on each side. So it was like this before the shift. So it went from 1, 1 to 1, 3 for that point. So it looks like it had a vertical shift by a scale of 3. So really it went times 3. And then it got shifted to the right by that minus 1. So that's where that tricky part comes in. So I really have y divided by 3 for that vertical shift of 3 equals x minus 1 squared. Or, remember, I could have that 3 on the other side. I could have said y equals 3 times x minus 1 squared. I could just multiply that 3 over. It's a little bit easier to see with the y's because I think this one's going to take us the most time and be the most difficult. So don't be afraid to ask questions here.